In this video, I would like to discuss what can be done with a circle and a point which is external to the circle. So consider that there is this circle and it has a radius r. So first we will be doing pure geometry without the help of coordinate system, which was developed possibly by René Descartes maybe. And so we will not be going into coordinate geometry. First we'll see what kind of geometry we can do here. So we have a circle and then we have a point which is outside the circle. Let's call this point P, and the center of the circle O. Because we have a circle, we also know its center, because using the center and a constant radius r, we can draw this circle. So we have basically one circle and 2 points now. What constructions follows from here? So one, obviously, like you can join these 2 points P and O, so you get this line, and there are 2 more lines which you can draw here out of nowhere. This is interesting. Can you see? You have no points now. You had 2 points, you have joined these points, you don't have any points now, but now what you can do is you can draw a pair of tangents to the circle. Let's call this distance d first of all, and you have these 2 lines here, 2 tangents. When you draw these 2 tangents, you also get these 2 new points, which are the points of contacts, and let's call them A or B, and then you can draw a chord of contact. This is called a chord of contact. Why? Because it is a chord to the circle and it's joining the point of contact of the tangent to the circle. So this is a chord of contact. You have a new line now, and you have this point. What more you can do here is, like, you can connect these 2 points now also, and this is just a radius, another radius of the circle, and these 2 points also, and I think that's it. Yeah, I think that's it. And some features, you see that this radius is perpendicular to the tangent. This is a very interesting issue which on which I would like to do another video sometime, but let's say we know that radius is perpendicular to tangent, so we have these 2 angles 90 degrees. So we have this kind of construction, and I don't think we can do more here. We can do more, of course we can do much more, but nothing too simple. I mean, you have this triangle here, so you can draw a circle which will be circumscribing this triangle, and so on. You can go on constructing. Geometry is all about constructions. You have another point here also, right? And I think all these points have been connected in the usual way. So that's it. And now you see, when we had a point and a circle, we had these 2 distances r and d, and whatever construction we have done here has naturally followed from the position of the point and the circle. So all the lengths which can be calculated here, like let's say the length of the tangent, let's say that this point is a, so this length PA should be determined in terms of D and R, because all of them have this length has naturally followed from the length D and R. There's no more information required to figure this length out. So that is very important when you're doing geometry or any kind of situation. What follows from what is very important. So you should be able to, first you should have an idea that we should be able to measure these lengths, and then only you can devise a method to do that, right? So mostly I see people are using mathematics without understanding what will happen next. So that's disastrous. Anyway, so let's call these points A and B, and then let's try to figure out these lengths. PA, PB, you can feel that this PA length and PB length would be equal. AB length is pretty interesting. It's the length of the chord of the contact. That should also be determined using D and R only. So how are we going to do this? Before that, we can mark this point here also, some point, let's say M, and then we can say that we can also find AM and BM. They are nothing but half of AB, as you can feel, but we haven't yet proved it rigorously, but we will do it. AM and BM, and then we can also find out OM and PM. That would also be interesting to figure out, OM and PM. Let's see how we can do this. So I think you should see some congruent triangles here. So for that, these are the two radius, OA and OB. So let's mark them R. And then, okay, because this is a right angle triangle, you can figure out this length using the Pythagoras theorem. You can apply this Pythagoras theorem on AOP and similarly on BOP to figure out these two lengths. As suspected, P and PB would be equal, and they are equal. It has been proved by Pythagoras theorem now. Okay, what more? How about this? These angles here, are they 90 degrees? They feel pretty much like 90 degree, and because of symmetry, you see that this is a line of symmetry, and it feels like not pretty clear. Okay, so let's try to see through some geometrical ideas. So let's say that this angle is theta, this angle is theta. Yeah, I mean, both of these angles should be equal, right? Because in the right angle triangle, let's say if you are thinking about triangle AOP, then from here, if this angle is theta, you can write sine theta as perpendicular, which is r, by hypotenuse d. Sine theta is r by d. Similarly, let's say if this angle was alpha, but if you write this sine alpha in the triangle BOP, you will get the sine alpha will be same, right? Perpendicular by hypotenuse r by d. And that's why this alpha and theta would be equal, because this alpha or theta, whatever this is going to be acute. You can move this point like in whatever direction, wherever you want to have this, just keep it external, and you will see that these angles are going to be acute. So these two angles are equal, and then because of that, this angle is 90 degree minus theta, and this angle is also 90 degree minus theta. And okay, let's see. So we are going to think about these smaller triangles, AOM and BOM. AOM here and BOM. So this triangle and this triangle. Okay, so what can you see here? You can see that the R, this is equal. You can see that this side is common, and you can see that the angle between these two equal sides is equal. So by SAS, you can prove that these two triangles are congruent, right? These two triangles are congruent by SAS. This means AMO is equal to BMO, and also they add up to 180 degrees because they are on a straight line. So these two angles should be 90 degree, AMO and BMO, which are so here you got these 90 degree angles. Okay, so pretty rigorous, right? Like, that's interesting. That's one of the nice thing about geometry. It has to be rigorous, and you can't reason from the statements which follow, which does not follow from the simpler thing. I mean, sometimes you are reasoning in a way which is not in a proper order, but I think in high schools we get a very good introduction of geometry, what follows from what. So I myself haven't read the book Elements by Euclid, but I have a pretty good idea what would follow from what. And okay, so because of this congruency, now this is 90 degree. Because of this perpendicular, these angles being 90 degree, this was 90 degree minus theta. So these angles are theta. Okay, so now what do we get here? We get three triangles. If we can see three right angle triangles, a big one, APO or BPO. So I have taken only APO here. APO, it's a right angle triangle with one angle theta. Then you get another angle AMP. let's take a look at this. AMP, it's here. No, sorry. AMP is not the smallest one, is this one. AMP. This is also a right angle triangle with one angle theta. And AMO, the smaller one, this is also a right angle triangle with one angle theta. And we can calculate in APO, like in the bigger triangle, the biggest one, we can see that we know all the lengths. These triangles are definitely similar because of all the angles being equal. But in triangle APO, we know all the lengths, and we know that this length is r, this is d, and this should be therefore root under d square minus r square. So from there you can calculate sine theta, cos theta, and tan theta, and use it in these triangles to figure out the rest of the sides. That's the idea. So let's do it. What do you know in triangle APM until now? APM, we know AP, we don't know AM, and we don't know PM. So we know only AP, which is root under d square minus r square. What do we know in AMO right now? We know AO is r, and do we know any other thing? No, nothing. So we know r. So now sine theta we can write from the first triangle here is r by d. From there you can also write cos theta. And then now we can go on to figure out all these required lengths. We will be reaching till AB using this AM and BM. So I think tan theta also we can write, of course. So let's see, AM is equal to r cos theta. How? So take a look at this triangle here. If this is r, then the base should be r cos theta, right? So, or you can also go into this triangle. We are talking about AM. AM is also here. If this is root under d square minus r square, this is the perpendicular. So you can also write it as root under d square minus r square into sine theta. So whatever you use, if you use cos theta, you will get this thing inserted here. If you use sine theta, you get these things inserted here, and of course they would give you the same result, r times root d square minus r square by t. So we've got AM, so therefore we've got AB, which is twice of this length, right? And then AB, BM, and AB, AM, BM has been done. Now we are on to MO and PM. So you see MO is here and you see PM is here. That's very simple to calculate. So what would you do now? PM, we can use, we can go in this triangle. PM is hypotenuse times cos theta here, because this is the base, right? So we can calculate base using cosine. Hypotenuse times cos theta is base, of course. And then you got the PM. So you put the value of cos theta from here, and you've got this PM. Okay, how about now OM or MO, whatever you call it? MO is r sine theta. This is the perpendicular relative to this theta. So r sine theta, you've got it as r squared d. So we have got a PM and OM also. So we have calculated all the lengths and all the angles because of that. So you see, if something follows from something, some given information, then they should be deterministic using the previous information. That's the lesson here. You can also verify that PM and MO should add up to PO, right? So PM, you check this PM and you add MO. So you see d r square will cancel out and you will get d square by d, which will be d. So consistent also. Okay, so once we have done this kind of geometry, I would say that the most important point here was this similarity of these triangles. You can see these three triangles hidden there with right angle triangles, and all of them are similar. So that's the most important thing here in terms of calculations which we have done. Okay, so now we will go into coordinate geometry, and we will therefore bring in algebra. And I hope my viewers know the basics. So I would like, it's mostly targeted towards students who are preparing for JE, advanced and mains examinations. So and any high school student should also be be able to understand whatever I would use, some results I would use. So basic coordinate geometry of circles, if you know, and then if you want to explore this, ss1 is equal to t1 square, and other things like, you know, like what is t1 is equal to 0, without actually going into pole and polar. I would try to make it more easier. So if you know about these things, please proceed, and if you want some more clarification into that. So this is the circle, and this is an exterior point, and we have this pair of tangents, we have this line connecting the external point and the center of the circle, we have this connecting radii, and then we have this chord of contact. And what I want to figure out now, what information do we have in terms of coordinate geometry? What information is given? If you know the circle, you know the equation of the circle, and you should know that the equation of the circle should be something like this. And if you know the external point, you should know the coordinate of this external point. If you know the circle, from this equation you can figure out the radius of the circle and the center of the circle. So in this it's hidden, like this would be minus g minus f, and radius would be root under g square plus f square minus c. And you will say, how? So this is what I expect you to know. Okay, so then now we don't know any other thing. So now from here, at this point, I would call it A, and let's say that its coordinate is x2, y2. We don't know it yet, we only know these two informations, okay? And B, we don't know about this thing right now, but we would figure them out. Center, we definitely know this. And this equation of circle, it can be written as sxy is equal to 0. This expression here, right here, we can write it as sxy. It's just a symbol, like you have fxy, a function in x and y. So this is like a sxy, a kind of a function in x and y, which is a polynomial of degree 2 in 2 variable, something like that. So sxy is basically this expression, right? And if you put it equal to 0, you get the equation of the circle. So we have sxy, and then this would be important for us. And if you differentiate this equation of circle, and you calculate this dy by dx from here, you get this slope of this curve. And if you take a point x0 y0 on the circle, and these points are different, okay, I'm talking about some other general point x0 y0 on the circle. So if you take another point x0 y0 on the circle, let's say somewhere here, and you put this x0 y0 in this expression, you will get the slope of the tangent there, right? And then from there you can figure out the equation of the tangent. So the slope of tangent is written here, and then if using a general point on the tangent, so if you have a tangent, let's say that the general point xy here is on the tangent, you can also write this slope using y minus y0 and x minus x0. This will give you an equation of the tangent in terms of x and y. So if you multiply this, you will get y y0, and this whole expression, this guy gets multiplied here. So you get y y0 fy minus y0 square and minus y0 f, and this thing gets multiplied here, so you get this expression. Now what do you see here? You see x0 square, you see a minus y0 square, you would like to move it to here, right? Yeah, you would like to move this y0 square to here. Why? Because this point x0 y0 is on the circle, it should satisfy the equation of the circle. So you get this expression that x0 square plus y0 square plus 2gx0 plus 2fy0, sorry, plus c is equal to 0. And if you can make this expression, you will get a 0. So that's tempting. So we'll try to rearrange this equation in such a way that we make this expression on the RHS, which can be done. I have an gx0 here, I will have to add a gx0 on this side also and this side also. So this side, the added gx0 is here, you see gx0, and here I make a 2gx0. So just readjusting this thing, and this whole expression will turn out to be 0. So we get a very nice expression here. and this is the equation of the tangent. It can be written as, now there's another, this very important expression here, uh, this expression, this is t x naught y naught x y. This, what is this? I mean, what kind of a notation is this? This is some linear equation in x and y, as you can see, but it has been written according to the point x naught y naught by transforming the equation of the circle. How has the equation of the circle transformed? X square has become xx naught, y square has become y naught, 2x. If there is a x, you can always generate a 2x there by dividing and multiplying by 2. And 2x has been transformed as x plus x naught, and 2y has transformed as y plus y naught. And that's it, these terms. If there would have been an xy term, you could have made it 2xy and transformed it as xy naught plus x naught y. How do I know that this kind of transformation is happening? So for this you will have to go into the details of pole and polar, which I am not going to go into, but this is very interesting to understand this expression. T x naught y naught is we have transformed these terms in the equation of the circle according to x naught y naught, as you can see here, and we have replaced them by x square by this xx naught. So the quadratic equation, equation of the circle, which is in degree 2, now becomes a linear equation. And if you do this kind of transformation according to x naught y naught, if that x naught y naught is on the circle, then you will get the equation of tangent through that point. So understand this t is going to be very important. This is a linear function, and it has been obtained by transforming the equation of the circle according to this point. And if this point is on the circle, then this equation, this equation, if you put this t to be 0, you get the equation of the tangent. Okay, so by far we know we have sxy is equal to 0 if we have a point on the circle, and if I transform this equation of the circle to t x naught according to this point x naught y naught into a linear equation, this t equal to 0 will give us the equation of tangent. Okay, I know we are here constructing some expressions, and this is actually done to simplify your calculations, because if you have been doing coordinate geometry and you have been solving some difficult questions, you would be aware of the fact that sometimes the solution gets too cumbersome, and sometimes you get a lot of connections, and you might get stuck. But if you know about these expressions, you can proceed faster and you can improve your coordinate geometry skills. Okay, let's move on. Sxy is this expression, and t xy according to x naught y naught is this. Okay, let's move on. Moving on to what? So moving on to the equation of the chord of contact. We don't know this point yet, x to y to, and we will not be solving algebraically for these points using by substituting, by solving two simultaneous equations and whatnot. We'll use a very interesting logic here. So if this PA tangent will have equation t x2 y2 xy is equal to 0, right? Because x2 y2 is on this point, is on the circle, and you write t, the tangent expression, at x2 y2, and you get this. The PB tangent will have this equation x3 y3, the t written according to point x3 y3, and you will get this tangent. We have already proved it. Now what? So this PA tangent passes through P, so therefore you will have t x2 y2, and here for xy, if you put x1 y1, you will get that this point x1 y1 will satisfy this equation, so this will be equal to 0. And just take a look at this, t expression right now. and we are putting x2 y2 here, so this expression, no, we are putting x2 y2 in place of x0 y0, and you are putting x1 y1 here. Okay, so this expression, you use this, and you'll get this x1 x2 y1 y2 x1 plus x2 y1 plus y2, everything is symmetric. And you can say that this is like t x1 y1 and x2 is equal to 0. You have you see this is your t here. You can verify that this is true. So this is pretty interesting. If you have like t according to some point alpha beta, and let's say ab is equal to 0, you can say that tab alpha beta is equal to 0. That's a very important property of this expression t. Okay, so we have this, and then we will do it. PB passes through point P, so this t x3 y3, this is the equation of the tangent. You put x1 y1 point here in this, and it should satisfy. So because of that, and then again because of this symmetric relation, x1 y1 you can put here, x3 y3 you can put there. Now what happens is you see the t x1 y1, imagine this equation. This is t written according to point x1 y1. X1 y1 point is not on the circle, it's outside. But just imagine that t x1 y1 xy is equal to 0. I mean, it will not give you a tangent which is passing through P, because it doesn't make any sense, because P is not on the circle. What is, so imagine this equation, you are writing t according to the point x1 y1, and this is not going to give you a tangent. What is it giving you? So if you look at these two circled expressions here, this is, first of all, this expression which we have written here is a linear equation, right? This expression is a linear equation, and it is being satisfied by 2 points x2 y2 and x3 y3. What does this mean? It's an equation of a line passing through the point x2 y2 and x3 y3. These 2 points, equation of the line passing through x2 y2 and x3 y3. So which is the chord of the contact? So this equation must be the equation of this line, right? Pretty interesting. So if you apply t on some exterior point, you get the t is equal to 0 on some exterior point, you get the chord of contact. Don't get a tangent, you get the chord of contact, and that's a unique line also, chord of contact. You don't get any of these tangents from the pair of tangents which are going to the circle from this point. You don't get any of this, neither this, you get neither this. You get, what you get is the chord of contact. Pretty interesting. So we have the equation of chord of contact now. Okay, now we will be focusing on the equation of pair of tangents we haven't got yet. So this is a point P, this is a circle, Sxy is equal to 0, and this chord of contact will have this equation t written according to point x1 y1. But how do we get the equation of pair of tangent? You see that this equation here, the equation of circle is of second degree. The equation of this chord of contact is of first degree. And if I conceive, okay, so first of all, you see this t x1 y1, instead of writing this x1 y1, I will just write 1 now, okay? It would save us some time. So t1 xy is equal to 0 and this sxy is equal to 0. These are the equations of the chord of contact and circle respectively, and then we can, using these two equations, we can construct, and now we construct algebraically, okay? We construct two expressions, sxy plus lambda. Lambda could be anything, it could be any real number, and equation like this, it's a second degree equation constructed according, using this sxy and t1 xy tau. And so you see this point here and this point here, which we were writing as a x2 y2, and this point was b x3 y3. So the point a x2 y2 satisfied this sxy is equal to 0. It also satisfied this t1 xy is equal to 0 because it lies on the chord of contact and also on the circle. So if you put it in this equation, it will satisfy. So this equation is satisfied by point A and similarly also point B. So this is the equation of some curve or something which is passing through A and B for sure. And this is a second degree equation once again, if you can see, because this is second degree and this is a linear, so eventually it is second degree equation, so it could be a second degree curve, right? Similarly, we can construct another second degree equation, because you see like t1 xy you are taking just as a linear function. You can also square it, and the degree of this expression also, this equation also, will not go beyond 2. This is another second degree curve which is satisfying these 2 points. And our pair of tangent is a second degree curve which passes through these 2 points. It also passes through x1 and y1. So that we can, I mean, any of these construction can give us the pair of tangents. I'm not saying that it will give us, but it can give us. So let's recap. Both of the equations are of second degree curve because the degree is 2, and both are satisfied by x2 y2 and x3 y3, these 2 points here. Okay, let's analyze the first one. Sxy is equal to 0. You have like this is like x square plus y square plus 2gx plus 2fy plus lambda times some linear function. This is linear, right? So it's like ax plus bx plus c. And what happens that you will have in this equation, your x square and y square coefficient will be equal, and you won't get any xy term. So this is, what does this indicate? That this is going to be the equation of a circle? Yes, this is equation of a family of circle passing through point A and B. Okay, so what can we do from here? We can extract a very interesting circle which is passing through P, A and B using this equation. This kind of a circle we can extract. For that we will have to make this equation if the circle also passes through P x1 y1. Just put x1 y1 in this equation, and if that's satisfied, figure out what lambda would be in that case. So sx1 y1 and t1 x1 y1. Okay, so what is this? This is sxy. When you put some point inside it, let's say x1 y1, if you put some point inside it, it would be 0 only if this x1 y1 lies on the circle. But if here you see that x1 y1 is outside the circle, in that case it will give you a positive value. That means that the point is outside. I hope my viewers also know about this. So x1 y1, if you put inside it, the expression what you get is normally called s1, because you have put you put x1 y1 inside this s. So you can call that s1, and use it lambda t1 x1 y1, t1 x1 y1. If you, for x0 y0 you put x1 y1, and for xy also if you put x1 y1, you will get again the same expression as s1. So that's why this transforms as this, and lambda is equal to -1 in this case, because s1 is not going to be 0. It's going to be a positive number as the point is outside the circle. So s minus, for lambda we can write, just simply we can write s minus t1. Now I am also ignoring this xy function because I think you are now familiar with this. So s minus t1 is equal to 0. This is the equation of that circle which we are looking for. This one, this is a very interesting circle, and from here many other constructions will follow also, but this one is nice. But unfortunately we didn't get the equation of the pair of tangent from here, so we hope to get it from this second expression. Okay, just let's, what the heck is this? Because in this the x square y square term will also come from this part, and this will make it a little bit complicated. Some second degree curve passing through A and B. What kind of? It's hard to tell. Okay, so let's analyze a little bit more. Let's first make it pass through x1 y1, because we want to get the equation of pair of tangent, and let's make it pass through x1 y1 at least. So what do we get for lambda? So we put x1 y1 here. This will be s1 square. This will also be this will be s1. This will be s1 squared. So you solve for that and you get lambda is equal to minus s1. You put it inside this expression and you get this thing, ss1 is equal to t1 square. And if you have seen this result, you know that this is the equation of pair of tangent, but we just have to prove it that it is so. How do we prove it that it is so? Might be the pair of tangents. I mean, we just have to prove it. Now how do we do that? So what I'm going to do to prove it is like first of all realize that this is not going to be a circle, this is not going to be a point, and this is not going to be nothing. Sometimes you have this second degree equations which represent nothing. For example, x squared plus y squared is equal to minus 9 will not be satisfied by any point in the R2 space. So it's not like that, because this circle, this equation is already satisfying these 3 points, so nothing is cancelled out. Point is cancelled out because of the same reason, because it is being satisfied by 3 points, so it's not going to be just a point. Circle is cancelled out. Why? Because we have already had a circle which the equation of which was s minus t1 is equal to 0, and this is definitely, it looks like a different equation. So this is not going to be a circle. So this is either a parabola, ellipse, or hyperbola, or a pair of straight lines. But how do you prove that this is, I mean, how do we know that this is a pair of straight lines? So suppose your origin is here, you transform your origin, you take your origin, shift your origin to this point P here, and in that case, if this is a pair of straight line, then you will get a homogeneous equation. This is my idea. So in the new coordinate system, your x is x minus x1, y is y minus y1. So let's transform this equation in such a way. So you have ss1 is equal to t1 squared. It actually means sxy, and s1 is t1 xy squared. So this is your equation, right? You just put it here, you transform it. X is equal to capital X is the new, X is coordinate in the new system. So from the old system you have x is equal to x plus x1 and y is equal to y plus y1. This is the connection. So you can just substitute, respecting the equality, you can substitute this x and y here to transform this equation in x and y. It gets a little bit cumbersome, but I know, but just take a look at this. No, we just have to prove that the coefficient of x and y and constant term vanishes. So this is like 0 times x, 0 times y, and constant term also becomes 0. Then we will get a homogeneous equation. So just do a little bit of calculation. So open up this part. So you get a x squared, y squared, you get 2gx1 and 2gx1. You get a 2gx from here, okay, which is here, and you get a 2x1x from, okay, this expression. Similarly for y, and okay, take a look at this. We have got an s1 here also, just out of this c. Is it possible? No. You are getting an x1 square from here, you are getting a y1 square from here, you are getting a 2gx1 small x1 from here, you are getting a 2fy1, and plus c, that makes up for this s1. And similarly on the other side, you can explore what is happening here. Let's see, x plus x1 into x1. So you're getting an x1 square, you're getting a y1 square, you're getting a 2gx1, you're getting a 2fy1 and c. So that will account for this s1. And besides that, you get xx1 and you get gx from here. So g plus x1x, and similarly f plus f1y, and that is whole squared. Okay, so verified. And then now you open it up, so you see that the coefficient of x and coefficient of y and the constant term here, and you see the coefficient of the x term, the y term, and the constant term here, they all get equal, and then they will get cancelled out, and what you get is a homogeneous equation which proves that this is a pair of straight line, and this is the equation of the pair of tangents which we are looking for. Thank you.